Assalamualaikum and greetings to everybody. My name is Alif Hisham bin Hamsul. My matrix number is 05 DAD 22F 2005.
Okay, good morning, sir. My name is Azik Munan Anak Chair, and my metric number is 05 DAD22F 2014.
Okay, good morning to my lecturer and my fellow friend. So today I will present about vehicle dynamic based on our car model. So vehicle dynamic is a study of how vehicles move, particularly how they respond to driver inputs and external forces. It involves analyzing the force and motion acting on a vehicle to understand and improve its performance, safety, and comfort. This field combines principles of physics, mechanics, and engineering to explain behavior such as acceleration, braking, cornering, and stability. Key areas of vehicle dynamics include longitudinal dynamics, acceleration and braking, lateral dynamics, cornering and turning, and vertical dynamics, ride quality and suspension behavior. Understanding this dynamic is crucial in the design and development of vehicles from every passenger cars to high-performance racing machines. Engineers use simulation, mathematical models, and real-world testing to optimize vehicle characteristics like handling, traction, and rollover resistance. Ultimately, vehicle dynamics help ensure that vehicles perform predictably and safely under a variety of driving conditions.
Okay, next this is our car data. Our the chosen car for our presentation is Mitsubishi Lancer Evolution X or Evo 10. This is the standard picture or the spec for this car.
The objective of this study is to analyze and evaluate the dynamic behavior of vehicle under various operating conditions by applying the fundamental principle of vehicle dynamics. This includes assessing longitudinal, lateral, and vertical response to driver inputs and external force. The aim is to enhance understanding of how design elements such as suspension system, tire configuration, and aerodynamic components affect handling, stability, safety, and ride comfort. Through simulation, theoretical modeling, and case analysis, the study seeks to support the development of vehicles that perform reliably and predictably in real-world scenarios.
Okay, classify the modification needed to reduce aerodynamic drag and increase fuel economy. First one is in the quest to enhance fuel economy. Various aerodynamics modifications can be employed on vehicles, each designed to minimize drag and improve overall efficiency. For example, one of the most recognized modifications is the installation of spoilers. These devices, typically mounted on the rear of a vehicle, help to reduce lift and drag by altering the airflow over the vehicle's surface. By redirecting air upwards, spoilers can facilitate increased downforce, which in turn enhance tie grip at high speeds, indirectly contributing to improved fuel efficiency. The Evo X stock rear wing creates significant downforce but also increased drag. Removing it or replacing it with a low drag ductile spoiler help reduce resistance. Another effective aerodynamic modification is the use of front splitters. These are extensions placed at the front of the vehicle that optimize the flow of air beneath the car. By decreasing the amount of air that goes underneath, splitters help to reduce lift and drag, allowing for smoother airflow over the body. This will result in better handling and can also contribute to better fuel economy during highway driving. Air dams are yet another modification that serve a similar purpose. Positioned at the front of the vehicles, air dams work to obstruct airflow that would normally cause turbulence. By streamlining the air that passes under the vehicle, air dams can significantly reduce drag, ultimately leading to enhanced fuel efficiency.
So I will talk about the question 4. The question 4 is use tire data calculator in BND Texas website to find tire stiffness and calculate suspension stiffness using the formula. Analyze the vehicle: A. Front and rear axle ride rate, and B. Front and rear axle natural frequency in Hertz. So for A, the tire size is from the car data, the stiffness is from car data, and then use the BND Texas to calculate the spec tire stiffness rate and get the 29.7 kilogram per millimeter. So we want to find the front and rear axle ride rate. So for the answer, front axle ride rate is 35984.89 Newton per meter. For the rear, the answer is 34766.06 Newton per meter. So for question B is to find front and rear axle natural frequency in hertz. So for front axle is 0.94 hertz, and for the rear axle is also 0.94 hertz.
Next, I will explain the question number 5. This is the calculation that I have done for determine vehicle inside and outside steer angle using Arcman geometry illustration. As you can see, the formula I used to find the inside is tan theta L per R minus T per 2. And then for outside, tan theta L per R plus T per 2. The difference is for inside the minus, and then for the outside the plus or something like that. As you can see, I already done the calculation, and then I have illustrated the Arcman geometry. Alright, next it is the advantage and disadvantage of tire change based on a review of a tire specification. The first advantage is handling. Better grip in dry condition, improve cornering stability. The second one is braking, shorter stopping distance on dry road. The third one is steering response, faster and more precise and response. The fourth one is aesthetic. It has sporty look with a low profile tire. Next is the advantage. The first one in wet or cold condition, it reduces performance in rain or low temperature. The second one is ride comfort. Harsh ride due to stiffer sidewall and lower profiles. The third one is tire wear. If it use softer compound, the faster it wear. The fourth one is fuel economy. Higher rolling resistance may reduce efficiency. And the final one is cost. Can the performance tire tend to be more expensive.
So discussion. So the first question is what makes the Evo 10's handling so sharp and precise? So the answer is the Evo 10's handling powers come from a combination of a stiffened chassis, advanced suspension setup, and Mitsubishi SAWC Super All-Wheel Control System. The suspension McPherson strut in front and a multi-ring rear offer excellent control, while the chassis rigidity help keep body movement tight. Most importantly, SAWC actively manage torque distribution for maximum grip and stability through corners. So for question 2 is how does the SAWC system enhance driving dynamics? So the answer is SAWC integrates four systems. For the first one is SCD, Active Center Differential. So this SCD is balanced torque front to rear. So second is AYC, Active Yaw Control. So this AYC send torque side to side in the rear for better cornering. So for the third one is ASC, Active Stability Control, and ABS, Anti-Lock Braking System, work in conjunction. Together, they are allowed the car to respond to driver input and road condition with impressive agility, offering excellent control in both dry and slippery conditions. So for the third question is, does the Evo 10 offer good steering feedback? So the answer is the steering is quick and accurate, especially during high-speed cornering. However, some enthusiasts feel the electric power steering lack the pure mechanical feedback of older Evo models that use hydraulic system. Still, the precision is top-notch for its class. So for the fourth question is what role do the suspension and brake play in its dynamic? So the answer is the Evo 10 suspension with Bilstein dampers and a back spring in MR trim provide excellent body control and keeps the car flat through corners. Paired with Brembo brakes, it stops hard and consistently even during aggressive driving or track use. Control in both dry and slippery conditions. So for the next question is how the how does the Evo 10's weight distribution affect its handling? So the answer is it has a front heavy layout approx 60 per 40, which typically leads to understeer. But the SAWC system and AYC torque vectoring help mitigate this by shifting power to the rear and side to side in real time, allowing the Evo to rotate more like a RW car when needed. So for the last question is how does it perform in different drive modes like tarmac, gravel, and snow? For so the answer for tarmac mode prioritize grip and precision on dry pavement, sharpen steering, and throttle response. For the gravel mode, soften response and optimize AWD for looser surface, reducing wheel speed. So for the third is snow mode. Prioritize stability and traction control for low grip aggression. This mode alter how the SLWC system behave, optimizing the Evo dynamic for various surface conditions.
For the conclusion, vehicle dynamics is the study of how a vehicle moves in a response to driver inputs, road conditions, and external forces. It encompasses the behavior of the vehicle in terms of acceleration, braking, cornering, and stability. Understanding vehicle dynamics is crucial for designing safer, more efficient, and better performing vehicles. Through the analysis of key elements such as suspension system, tire characteristics, weight distribution, and aerodynamics, engineers can optimize handling, comfort, and control. With advancements in technology, including electronic stability control and active suspension, modern vehicles have become more responsive and safer than ever. Ultimately, mastering vehicle dynamics leads to improved driving experiences and contributes to the development of autonomous and intelligent transportation system. Okay, this is the reference. Okay, that's all from me. Thank you.